Hi, and welcome to this video on predicting x-intercepts of quadratic equations or quadratic functions. Okay, so in this video, we're going to extend our study of the quadratic formula. So yesterday, we learned about the quadratic formula, and we learned that we could use the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we learned that we could use this formula in order to find the x-intercepts, or what we also call the real zeros, or the real roots. Okay, so this helps us find x-intercepts, which is a word that we're familiar with, but what we may not be familiar with is the fact that they're also called real zeros, meaning that you're finding the value of x when y is 0, and also roots. Okay, so real roots, which just means that you're finding the value of x when y is set equal to 0. So roots, sorry, that looks like roofs. Okay, so how do we go about that? Well, we have something that helps us determine whether or not we have x-intercepts or real zeros or roots before we actually go through the process of solving using the quadratic formula. So before we go through all that long quadratic formula, we want to make sure that we even have roots to solve for. Okay, so there's some certain conditions that apply. We use what's called the discriminant. Okay, so the discriminant is this right here. And as you can see, it matches this little portion under the radical. So we pull that out and we use the discriminant to help us determine whether or not we have x-intercepts at all. Okay, so how does that help us determine? Well, if we use our coefficients and put it into the discriminant and the value of the result is 0, that means that we have no real x-intercepts or no real roots. If we use that formula and put our coefficients in and we end up with the value of the formula being equal to 0, then that means that we have one real root. And if we plug those coefficients into this formula called the discriminant, and we get a value that's greater than 0, then that tells us that we have two x-intercepts. Okay, so let's try that. Let's use this table to determine how many x-intercepts each equation has. So here in the third column, you can see a list of examples. So we'll start with the first example. And that example is x squared plus 2x plus 5. So what I'm going to do is list my coefficients. My coefficients are a is equal to 1, b is equal to 2, and c is equal to 5. And we get our coefficients when our function is in standard form. If it's not in standard form, remember that we have to put it in standard form. Okay, so let's use these values to determine if we have x-intercepts. And if we have x-intercepts, then we're going to go ahead and find them. Okay, so in this case, a is 1, b is 2, and c is 5. So I'm going to say b squared minus 4ac. So that would be 2 squared minus 4 times 1 times 5. And that's going to give me 4 minus 20. And 4 minus 20 is equal to negative 16. And negative 16 is actually less than 0. So what this tells me is that I have no real roots or zeros. No real zeros. Okay, so you could say that I have no real x-intercepts also. Okay, or you could say I have no real roots. Okay, so what that means is that this particular graph does not cross the x-axis. So perhaps it's something like this, or maybe it even crosses the y-axis. So maybe it looks more like this, something like that. Excuse me, let me get this correct. But what we know is that it does not cross this x-axis here. And this is our x-axis where we would find our x-intercepts. Okay, it may very well cross the y-axis, so it could have a y-intercept, but what we know so far is that it has no real x-intercepts. So in that case, we don't want to waste our time trying to find the x-intercepts. Okay, we don't want to waste our time trying to find the real roots. All right, because there are none. Okay, so now let's go to the next example. So in the next example, I have the equation or the function x squared plus 4x plus 4. Okay, so let's go ahead and find our coefficients. A is equal to 1 in this case, b is equal to 4, and c is also equal to 4. So let's put that in the discriminant. B squared minus 4ac. Okay, so b squared is 4, and squared, so 4 squared minus 4 times a is 1 and c is 4. Okay, so in this case, I get 16 and that's going to be minus 4 times 4 times 1 is also 16. And so I end up with 0, and 0 is actually equal to 0. So this tells me that I have one x-intercept. Okay, so how does that happen? How do I end up with one x-intercept? Well, what may happen is I actually find, if I actually were to find that x-intercept, so I can take that and put it into the quadratic formula to find out what that is. Okay, so let's go ahead and find that x-intercept. So since I've already done this and I know that this is what goes under the radical, I'm just going to do x is equal to negative b. So using the quadratic formula, plus or minus the square root of b squared minus 4ac, all divided by 2a. Well, I already have that radical part portioned out. So x equals negative b. B was 4, so negative 4 plus or minus the square root. And I already know that this portion here, the discriminant, is 0. All over 2 times a is 1. And so that gives me 4 over 2. And the plus or minus 0 will go away, right? Because that will go away, so I'll be left with just 4 over 2. I don't need to add plus or minus 0. So that tells me that my x-intercept is actually 2. So it's going to be 2 comma 0. So if I go to the point 2, 0, I know that we know that our axis of symmetry also passes through our vertex, right? So in this case, this is the middle of the parabola. But since this is the only root, the parabola will actually go up on each side. And I can see that my y-intercept, if I were to plug in 0 here, 0 here, then these would both be 0. And so my y-intercept will be 4. So 1, 2, 3, 4 would be my y-intercept, right? So then I know over here since the x-axis of symmetry is the middle and the vertex is the middle, right? Then my x-intercept is also my vertex in this case. So what I get is a function that looks like that. And you can see that it crosses the x-axis only one time. So this is my x-axis, this is my y-axis. And so that actually helps me get kind of a general graph. It's not the exact graph. We could probably find more points in order to make it a more perfect parabola. But generally, I have one x-intercept at 2, 0, which means that that x-intercept has to be the vertex. So if I go and plug in a 0 into this function, I find that my y-intercept is 4. And so I know that since a parabola is symmetric, I can also reflect that point over to the other side and get a general graph of what my parabola looks like. Okay, so now let us go to the next one. So b squared minus 4ac is greater than 0. Okay, let's do this case. So my coefficients are a is equal to 2, and b is equal to negative 7, and c is equal to 3. Okay, so what I'm going to do is use a discriminant to see how many x-intercepts I have, or if I have any at all. So b squared minus 4ac, so in this case it's going to be negative 7 squared minus 4 times 2 times 3. So negative 7 squared is 49, and that's going to be minus, so when I multiply all this together, it'll be 4 times 2 is 8, times 3 is 8 times 3 is 24. Yeah, 8 times 3 is 24. So in this case, 49 minus 24 is going to be, I think, 25. No, yeah, 25. Okay, so in that case, this is greater than 0. So this means that I have 2 x-intercepts. Okay, so I have 2 real x-intercepts, or 2 real roots. Okay, so in this case, I could actually go ahead and graph those. I could find out what they are using the quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So in that case, x is equal to negative, and we have negative 7, so negative 7, and that's plus or minus the square root. I already found the discriminant to be 25 over here, so I'm going to plug that into the quadratic formula because that's the part under the radical, all divided by 2 times, in this case, 2, because a was 2. So x is equal to 7 plus or minus, well, let's take the square root of 25. That is 5 over 4. And let's simplify that in this case. So I get x is equal to 7 plus 5 divided by 4. And x, here's my little ampersand, excuse me. And x is equal to 7 minus 5 divided by 4. So let's see what those are. Well, 7 plus 5 is 12. So 12 divided by 4 is 3. So x is 3, the point 30. And in this case, x is 7 minus 5, which is 2. So that's 2 over 4. So in this case, x is equal to 1/2. Okay, so at 1/2 and 3, those are my x-intercepts. All right, so I can go up here and find them. Okay, so let's go up and graph and plot these. 1/2 and 3 is what we said. So 1, 2, 3, and 1/2 is here. Okay, so I know that my axis of symmetry is going to be somewhere between these two. So right smack in the middle. Well, if I take the difference of 3 minus 1/2, that leaves me with 2.5, and half of 2.5 is 1.25. So if I go 1.25 in, so if I go directly to the middle of these 2 points, right, which will be like the average of these two, then I would, let's say 0.5 plus 1.25 would be about 1.75. So my axis of symmetry would be about here. Right, and if I know my y-intercept, so let's go and find the y-intercept so we can get a general graph. If I substitute 0 here and 0 here, those will both go to 0. So that will leave me with a y-intercept of 3. So let's go up 1, 2, 3. Okay, so I know that my graph does something like this. I don't know exactly where my vertex is, but I know that it's in the middle, right? It's somewhere between those two x-intercepts. Okay, because my parabola is symmetric and it's the same on both sides. So my parabola looks something like that. So in this case, you can see that it crosses the x-axis twice. So it crosses the x-axis once at 1/2, and it crosses the x-axis here at 3. So the goal of the discriminant was to actually help us find the x-intercepts of the parabola and to determine if it had any or not. Okay, so use this at your advantage. You can watch this video as many times as you want. I hope it helps. And I'll see you in the next video where we actually learn how to fully graph a parabola and find all of its important points algebraically. All right, thanks.